Okay, I'm gonna go over how to complete the Excel workbook. And this is as of I just re-edited it, took some stuff out and made it so that it's just a little bit more efficient. Hopefully this tutorial I'm going to go through from the beginning of it to the end of it. And so feel free to hit those different points throughout the video of, okay, now I need to go on to the next tab, the next tab, the next tab. So I'm just going to try to go through it all in one video and see if we can go from there. So I'm going to go ahead and share my screen and let's go. So first of all, you have right here the overview of the population for this versus the sampling distribution. This is just information on how to conduct calculations. Then coming in here, we've got a decision tree, and you can use all this information to be able to determine the correct answer about, for instance, the margin of error for confidence intervals, the sample size needed to calculate particular confidence intervals, so on and so forth. Then coming over here, pretty much the exact same thing, except this one gives you the opportunity to actually put the information in. Now, with your workbook, everyone's workbook is a little bit different. But what you have is you've got the population data, and so you've got a data set. What I actually did is I have, for a lot of these, I have the actual population data that is massively huge, and I calculated the actual population rating, the actual population height, the actual population, all of this. So this is, if it's not population data, it's very close to population data, because the sample size that I have is so massively large that most y'all's computers can't even actually handle how much data is in there. So I have the actual population data here for the majority of y'all. And then right here, what I did is I took a sample of, for instance, this is the NBA data. I have a sample of 150 observations. And so I put the sample data in here and the population data in here, and then this is just, the mean and the standard deviation. So that should say standard deviation population. And so then you come in here and you're going to have to actually calculate everything here. So now that brings us to our 3-1-1 distant error. For all of these workbooks, I have how to calculate everything down below. But for this in particular, you need to start with 3-1-1 and calculate the all of the summary information, or sorry, all the sample mean and the sample standard deviation, and all of this information about each individual category. And so we've got right here, let's see here, height in inches, height in meters, weight, pounds, kilograms, drafted round, draft peak, draft year, salary, and birthday. And so I put all the population information right up here, so that way you don't have to go back in and put the population information. And then right here, I want you to calculate the sample information. And so for height in inches, I do equals average. And then I come to the sample data and I go to height. And then I just do 71, and then you can press Control Shift down, and it should go down to the very last value. Okay, and so that gives me sample data, give me the average from this cell all the way down to the bottom. And so it's 78.5 ... And if you want to, you can use this fun little tool pushing it over to the right hand side, but really it's only beneficial to go to like 3. So if that makes your life a little bit easier, just going to 3. And so coming down here, the standard deviation of the sample, you pretty much do the exact same thing, equals standard deviation of a sample. And then coming into the sample data, you go to height, because that's what we're dealing with right now is height, and Control Shift down, and brings you down D2 to D151, and it gives you the information there as well. And I'm going to just go to 3 for everything. Okay, and then you do the same thing for height for meters, height for weight, or weight, so on and so forth, going all the way down. You just come over here, find the information in the sample data, and calculate the mean and the standard deviation. Then coming down here for our sample size, we use the formula equals count A. And what count A does in particular is it counts every single value in a particular range that is not blank. Okay, so we're going to go to height. And the reason why this is important is because some of y'all's data might actually have blanks. Okay, so for here, you've got 150. However, you come all the way down to, I don't know, say, let's see here, sample data, college. If we wanted to calculate, this doesn't have college, but you'll notice, I'm going to do this for college really quick, equals count A, and go to the sample data, and it'll have all these different blanks, and Control Shift down only goes down to the next blank. And so that's why you can't use Control Shift down when you've got a whole bunch of blanks in there. But you'll notice the colleges, there's only 131 observations that have colleges. And so that's why when you do count A, that's really important because it indicates the number that are blank. Next thing that you're going to do is calculate the sampling error, standard error, Z calc. In other words, you take a, what is the Z calculated of the sample compared to the population? And then T calc is what is the calculated T value of the sample mean compared to the population when we only know the sample standard deviation. Okay, so sampling error, we're going to do equals the sample mean minus the population mean. Okay, so that's the sampling error. The standard error is going to be equals, and you can come right down here, sampling error, standard error. So we have the standard deviation of the population divided by the square root of the number in the sample. So the number in the sample is 150. And so just close it. So now we have the standard error. Okay, next, Z calc. Okay, to calculate Z calc, we take right here the sampling error divided by the standard error. So we're going to do equals sampling error divided by standard error. And that gives us the Z calc. And very specifically, this Z calc, what that means is that Z calc is 0.17557 standard deviations above the mean. Oops. So that's what that Z calc is. And then T calc is a little bit different. So T calc is the sample standard deviation divided by the square root of n. So we're going to do equals the sampling error divided by, and then we're going to do essentially the standard error using the sample standard deviation. So it's going to be the standard deviation divided by the square root of the sample size. So what I just did there is the sampling error divided by the standard error, but this time the standard error is using the sample standard deviation instead of the population standard deviation. And then I'm going to press enter, and you'll notice that T calc is a little bit different. And then you just do that each time, and this is just to give you practice calculating all of this going all the way down. Next, we have 3-2-1. Now 3-2-1 is actually kind of broken up into 2 different parts. First of all, you'll have all of this information right here should pull from everything that you filled out here. So if you filled everything out here correctly, it will automatically populate in here. So that way you don't have to calculate it again. Okay. And so I've got height in inches, and we'll just go through this. So what is the standard error? So you already did this. So the standard error is equals the standard deviation divided by the square root of the sample size. Okay. And then also the standard error of when you use the what's that called? The standard error using a sample, you already did that as well. So that's the well, actually you didn't do this one. So it's the standard deviation, the sample standard deviation divided by the square root of n. Maybe you did. No, we did that right at the end, but we didn't make like its own little thing. And so now what we're doing here is we are, this really should say margin of error use the known population standard deviation. And then, you could pretty much say this is margin of error, use the sample standard deviation. Okay, so the way that we calculate the margin of error, we come down here, determine the mean estimate, the mean point estimate, desired, note the desired level of confidence. So right down here, it's saying we want a 90% confidence, 95% confidence, 99% confident, going all the way down. So we have 90% confident, which means that we're going to be using a z-score of 1.645. And so we do equals the z-score of 1.645 multiplied by the standard error. Okay. And so we've got the standard error right there. And just press enter. So then you're going to do, the 90% confident, and then the 95% confident, you do something very similar, equals the z-score multiplied by the standard error. Just keep going all the way down. So equals the z-score multiplied by the standard error. Oops. Now, the next one is a little different. And these are using t-scores. So if we haven't gotten to t-scores yet, we teach this on 2 different days. We teach this one on the first day, teach this one on the second day. And so this is using t-scores. And so to calculate a t-score, you come right down here. And so we use this fun little t dot inverse dot 2t. So that's what we're going to use in order to be able to calculate a t-score. And a t-score is determined by the sample size. So equals the t-score. Hold on. T dot inverse, there we go, dot 2t. And the probability. So the probability, it says 90%. So 90% right here, what that means is there's a 90% probability that the actual population mean will be within the confidence interval, the limits of the confidence interval. But the probability that we want is, what is the probability that the actual population mean will be outside of the confidence interval? So for right here, we're going to put 0.1, and then we're going to put the degrees of freedom. So the degrees of freedom is the sample size minus 1. Okay, so the sample size minus 1. Okay, or you could have put 149. Okay, and now what we're going to do is take that t-score, and we are going to multiply it by the standard error right here. What did I mess up? Let's see here. Oh, I put an extra equals. Yeah, that should work. There we go. So this right here is the margin of error, calculating the t-score, multiplied by the standard error using the sample standard deviation. So you do the same thing, equals t dot inverse dot 2t, and we're going to put the probability. So now there's a 5% chance that the actual population proportion is not going to be within that. So we're going to put 0.05 multiplied by or sorry, yeah, 0.05, and then degrees of freedom. And so it's going to be 150 minus 1. And then we're going to multiply that by the standard error using the sample standard deviation. And then you notice as your confidence level goes up, your margin of error increases. And then we're going to do this one more time, equals the t dot inverse dot 2t, and then put the probability. This time it's 0.01, because there's a 1% chance that the actual population mean is not within the margin of error limits or the confidence interval limits. And then the degrees of freedom, once again, 150 minus 1, and then multiplied by the standard error using the sample standard deviation. And there we go. And so what we want here then is the lower limit and upper limit for the confidence interval with a standard deviation known. And you'll notice these right here. These ones are going to be using the confidence interval of this standard deviation unknown. So you're going to be using these margin of errors for down here, and then you're going to be using these margin of errors for these up here. And so the lower limit and upper limit, what you're going to do is you're going to take equals the mean. So you take the mean minus, so for 95% confidence, and then we're going to do equals the mean plus the margin of error for a 95% confidence interval. And then you come over here and you say, I am, and I'm just going to copy and paste this. I am 95% confident that the actual population mean is between the values of, or values of 78.01 and 79.12. 79.12. Let's see. And that's how you go through this entire worksheet. And then coming down here, once again, you would use the values calculated in here. So you would use 99, you would use 90, and 95 right here, where right here you would be using 99, 90, and 95. Okay, next. Also, you can use these formulas, which is very similar. And so what you would do here is, instead of using, the 90% multiplied by the standard error, you would just do equals confidence dot norm, and then put the alpha of, once again, alpha is that probability, the alpha of 0.1, okay, and then the standard deviation of the, there we go, standard deviation, and then the sample size. So it's pretty much the exact same thing, but it's slightly more accurate, just because if you're dealing with any sort of rounded data, and then also it doesn't round this to 1.645, it gives you the true value that goes much beyond 1.645. And so you'll notice that it's slightly different, but it's different by what, 1/1000th, yeah, 1/1000th, so it's really not that big of a deal. Next, coming in here, you are going to be making confidence intervals around proportion. So for every single data set, you have to look at this information up here and say, okay, I've got to basically find the number of successes divided by the total number of observations. And you can find your total number of observations. You should be able to find it. For example, draft year, position, college, country, height, weight. They might not line up exactly with the category titles, but because you've got all these category titles right up here. but it should line up pretty quick, pretty easily. Like for instance, the bachelorette data, it says, you know, for the occupation categories of in the industry, beauty and fitness. So there are two different occupation categories. There's two different things. One says like occupation, the other one says industry, and you've got to go through industry and be like, okay, the industry of beauty and fitness. But what you're doing coming right here is you're going to insert a pivot table right there. And so we're going to go to the sample data. We're going to say insert pivot table. And then we're going to take all of this information right here, and it's going to go all the way down, make sure that it goes all the way down. And then we're going to go to 3-2-2. I'm going to go right here. Oops, I accidentally clicked on it too soon. Let's see here. Sample data, pivot table. Now go into an existing worksheet and then go to 3-2-2, come right down here, press OK. And so now we have to look at draft in round one. So I'm going to look at this and I'm going to say, okay, draft year. Nope, not draft year, draft peak, draft round. There we go, draft round. And it's 1, 2, or undrafted. And so I'm going to click, put it in the rows, put it right here. And you'll notice 1, 2, and undrafted. And then you'll see the grand total right down there. And so we do equals the number drafted in round one divided by the total. And so once again, 91 out of 150. And that gives you the proportion of 0.606667. Okay. And then you can do the same thing, draft year. Let's see. Let's do this one. Height, 84 inches or taller. So we come in here, and we'll do height in inches. Okay, and it goes into sum right away. We don't want sum. Summarize values by count. Yeah, this is great. 81 inches or 84 inches or taller. So what that means is anyone in these categories right here. So we do equals sum of those who are 84 inches or taller. And so there's a total of 12 people, 12 observations that are 84 inches or taller. And so what you do is you put 12. And then if there are 150 observations, we can check really quick. So let's look at height. And we can do equals count A. And yes, there are 150 observations of height. And so we'll do height. Let's see here. Height 150. And then we do equals 12 divided by 150. And that gives us 0.08. Okay, and so from 0.08, we can use these z-score values to calculate a 90% margin of error around around this proportion. Okay, and so this right here is a proportion or a percent. If you wanted to, you know, you really could be like, hey, let's change these to percent, you know, so it's 61% of individuals are drafted in round one, give or take, you know, 7%, give or take 8%, give or take 10%. Okay, I mean, it's rounded, but that's, yeah. So use the known population standard deviation to find the margin of error. And so what we're using is not necessarily the known population standard deviation, but we're going to do equals, and you come right down here. It should say use the known population proportion. So yeah, let's do z multiplied by the square root of the proportion, so 8%. So square root of the proportion multiplied by 1 minus the proportion divided by the number in the sample. Okay. And then this right here is the margin of error, and the 90% margin of error, which is essentially 3.64%. Coming right here, we use 95%, so equals margin of error. So we've got the z value multiplied by the square root of the proportion multiplied by, in parentheses, 1 minus the proportion divided by n. Okay. And then, so you'll notice the margin of error percent is, the margin of error is getting bigger. And then last but not least, equals the z-score for 99% multiplied by the square root of the proportion multiplied by, in parentheses, 1 minus the proportion divided by the sample size. Okay. And then coming over here, this is a 99% confidence interval. So what you're going to do is equals the proportion minus the 99% margin of error. Whoops. Equals the proportion. There we go. I don't want general. There we go. And then equals the proportion plus the 99% margin of error. And so once again, I just want, there we go. And then you can, just like we did before, which this concat, well, this one actually does work, but equals, you can copy and paste this from right up here. I am 99% confident that the actual population proportion is between the values of, I mean, you could do, let's see here, 0.0229 and let's figure out 0.137. 0.137. Okay, and so that's how you would go about doing that. And then right here, you would go into the next one, and then you'd get rid of height, and then just change it to whatever the next one is. So if it's draft year 2009 or earlier, position forward, you come in here and you're like, okay, which one is position? Height, rating, draft year, jersey. Okay, position. Then you got the year, the draft year right there. And so you just find the appropriate one. And then you find the number that meet this criteria divided by the total number of observations in that category. So next, we've got something very similar, the proportion, sample size, so on and so forth. All of this comes auto from the previous one. So if you filled in all of this, it comes over here and it fills in automatically for you. So we're just going to go right along with 84 or taller. And we're going to say, okay, we already knew a particular population proportion. If we wanted to assess it again, how large would our sample size need to be in order to be 90% confident at a particular margin of error? Or a particular maximum allowable error. So let's come right over here. So the z-score for a 90% desired confidence, it's going to stay 1.645 for all of them, and then 1.96 for all of these, and 2.576 for all of the 99%. And so the sample size that is needed, the way that we calculate the sample size is we've already got the z. We've got to look at the determined sample size. So it's going to be equals the probability, or sorry, the proportion multiplied by 1 minus the proportion multiplied by the z-score, except make sure that you put this in parentheses. I almost messed that up, equals, in parentheses, the z-score divided by the maximum allowable error. And then you take the square root of that. Or sorry, not the square root, then you square it. Okay, so this says if we want to have only a one, this proportion plus or minus 1%, or this proportion plus or minus 5%, this proportion plus or minus 10%. But this proportion plus or minus 1%, we need a sample size of 191. Well, not exactly. You actually need 1,991. You need to round this up to 1,992 because you can't have 0.6 of a person. Same thing for here. You need 258.28. Not exactly. You need 259 would be the correct answer. The same thing, you come right here, equals, and the sample size, the proportion multiplied by 1 minus the proportion multiplied by the in parentheses the z-score divided by the maximum allowable error, and then you raise that to second. Then you now need a sample size of 2,827.4 or 2,828. Last but not least, equals the proportion multiplied by 1 minus the proportion multiplied by the z-score divided by the maximum allowable error, which once again I forgot to put the parentheses in there. The z-score divided by the maximum allowable error, and then you square it. And so now we need 4,884 samples right there. And so we're going to come right here looking at the lower limit and upper limit. The way that you calculate the lower limit and upper limit, you have 0.08 minus 0.1 equals 0.08 minus 0.1 for the lower limit, and then equals 0.08 plus 0.1. And then what we get to say is, to be 90% confident that the actual population proportion is between these limits, I need a sample size of what? So to be 90% confident that the actual population proportion is between 0.7 and 0.09, I need a sample size of 192, or sorry, 1,992. Okay, and that's how you would go about doing that. So always round up. Okay, next. Last but not least, calculating the mean sample size, or sample size around a mean. We're going to use, you don't have to do anything with the sample standard deviation. I don't even know why I have this in here. I need to get rid of that for the future, but delete. There we go. So let's do the population standard deviation. And what we're going to do right here is height in inches. Yeah, let's do height in inches. And so we're going to do the known population standard deviation. How large does our sample size need to be? Unknown. Or sorry, the how large does our sample size need to be with 90%, 95, and 99%? Okay. So let's come down here, the population standard deviation, and yeah, just get rid of that. The thing is I used to require this, but the problem is okay, like you can calculate this based off of a previous sample that has been done and a sample standard deviation. And so it's like if you have a previous sample that's been collected and a previous sample standard deviation, you can use a t-score instead of a z-score. But I've just kind of made it so that let's just stick with the population standard deviation for everything and make everything a lot cleaner, and just assume that everything that we have for right now is dealing with a z-score and dealing with a previously known population standard deviation. So let's look at the height in inches. So we've got equals so we've got the maximum allowable error, but determining the sample size, the z-score of 1.645 multiplied by the population standard deviation, okay, then divided by the maximum allowable error, and then raised to the second, okay, which gives us, we need a sample size of 1. Just make sure that I'm doing this correctly. Z-score multiplied by, okay, and then that's all in well, that makes sense ish. The funny thing is, I messed this one up, but it is what it is. I said that I can have a maximum allowable error of 5. Well, my standard deviation is 3. And so because of that, my maximum allowable error being larger than my standard deviation, it basically calculates out to I need a sample size of 1 in order to be able to determine that. And I should have made the maximum allowable error smaller in order to have something that's a little bit more appropriate. Like if I were to have done the maximum allowable error of 1, oops, 1 instead, then that increases. And so that's a much more accurate. And so I'm just going to change it to 1 for the rest of these, so that way you can get something that is actually more appropriate. But now we're going to do equals the sample size, or sorry, equals z 1.96 multiplied by the standard deviation. Okay. And then divided by the maximum allowable error, and then we're going to square it. And so now 44, and then last but not least equals the z-score multiplied by the standard deviation divided by the maximum allowable error, squaring it. And so now the sample size needed is 76. So for the lower limit and upper limit, what we're going to do is equals the mean minus the maximum allowable error, and then equals the mean plus the maximum allowable error. And so what we're going to say is we're going to copy this to be 95% confident that the actual population mean is between, we're going to put 77.5 inches and 79.518. 79.518. We'll just put 518. I need a sample size of, so 95%, we're going to come right here, 44. Okay. And then you just go all the way down. And don't worry about this so much. I know that you just take whatever you did here, put it right there, and you know, plug in what it is that you need. And that's pretty much how you do all of this. Don't worry about the sample stuff. It can be used for calculating the needed sample size based on previous sample data. So if you were to use this, it would say, how do you calculate the needed sample size because you have previous sample data? And this would be, you know, what you use calculating the needed sample size because you have previous population data. But right now I'm just using all of this, everything like we have previous population data to keep things a little bit cleaner. So that's how you'd go through this entire workbook. Hopefully this was beneficial and answered a lot of your questions in one fell swoop.